Okay, good morning, everybody. Last time we spent the class period going over in considerable detail aspects of implementing and coding around linked lists. Specifically, what we were examining was the problem of how do you traverse a linked list? How do you do something relative to every value stored in that linked list? We already had, to some degree, been accustomed to thinking about this with regard to arrays, right? Conceptually, I think we were very accustomed to how to think about this with arrays. That is, you've got some kind of an index variable. That index variable lines up with a slot in the array. You can increase that index variable progressively. That in turn means that you're examining a different cell of the array. With a linked list, you can't do it quite the same way, because with a linked list, you are jumping all around the main memory of the computer. You're looking here, you're looking there, you're looking everywhere. And so it required thinking a little differently about what precisely it is that we were doing. In fact, it lent itself to two distinct approaches, an iterative approach and a recursive approach. The iterative approach, we see an example right here, is really rather similar to what we do with an array. The difference is, how do we set up what we're looking at? How do we figure out when we're done? And how do we advance to the next item? As long as we recognize that the same roles are present in traversing a linked list, we can plug in different operations that fulfill those exact same roles, and the structure winds up looking really similar. That said, the recursive definition of a linked list lent itself to a recursive implementation. And we saw an example of that right here, where the implementation mirrored precisely the structure of the data itself. What did we mean that the data is recursively structured? Just to review, if we look back at the top, an object of the node class has a data member, which is an object of the node class. And this is only the first of a number of data structures we're going to see that are going to have this kind of a structure. We're going to find that this is actually a fairly common idea, and it's going to pop up quite a lot. And a lot of the importance of the linked list is that this is kind of the simplest example we're going to see of a recursive data structure. All of that said, having seen that we can take both an iterative and a recursive approach to traversing a linked list, I want to turn it around just a little bit and think about what would it mean to take a recursive approach to traversing an array. So to that end, I'm just going to create, wait a minute, just a second. I really just want to create a simple little class. Not a whole, yeah, there we go. So I'm just going to call this recursive array demo. And just to keep things simple, set up a main. And inside this main, I'm going to quickly define an array. So I'll say something like int nums equals new int. And there's a syntax which isn't used hugely often in Java, but which is pretty convenient, where instead of saying I want an array with this number of elements, you can say I want an array with this list of values. And so I'm going to do that now. So let me go over the syntax just so you all are clear on it. I can say new int, and instead of putting a number in the square brackets, I can give it empty square brackets. And then I use two curly braces. And the comma separated values inside of those curly braces are going to be the values in the array. And the size of the array is going to be just the number of values that I put into the curly braces. So how big is this array? 6, yeah. So now what I'm going to do is I'm going to write a method that will recursively visit all the elements in the array and calculate their sum, which is something that we did for the linked list. So to that end, I'm going to create what's called a static method. What's a static method? It's a method that's not associated with any specific object. The reason I'm doing this is I don't need to create a new class for arrays. Arrays already exist. I just want to create a method that can operate on them. So I'm going to say public static int sum. And what sum is looking for is an array of ints. And so let's say I want to calculate this recursively. So in other words, I want to be able to do something like this. I want to say down here, system out println sum of nums. Like that. So if I'm going to do this recursively, what is my base case? That will be the value I return, perhaps. But how do I know if I'm there? That's right, if I'm at the end of that array. Conceptually, that's absolutely right. The deeper question is, how do I know if I'm at the end of the array? How do I know?
If the index you're looking up is one less than the length.
Okay. If the index I'm looking up is one less than length, or we might ultimately find equal to the length. Okay, which index am I looking up? Does anybody have any idea? You know what? I don't. I have no idea what index I'm looking at. No clue whatsoever. With recursion, all information about where am I in the process somehow needs to be expressed through the parameters of the recursive function. Let's jump back to our linked list so we can kind of see a contrast to this. If we look at sum in my linked list, how did I know where I was in the linked list? Deep down, how did I know which node I was at?
This node, sum of the rest of it.
That's right. So I'm at this node. Then I ask the next node to give me its sum. And when I ask the next node to give me its sum, the recursive call comes in, and next is now this. So the node I'm on is the node on which the recursion was invoked. So when we're dealing with recursion and an object, one way that might be helpful to think about it is the object itself is kind of an implicit parameter. And by jumping to different objects, you can be in a different place in the list. With arrays, that doesn't really work. So I'm going to have to do something unpleasant. I'm going to have to actually add a parameter. So I'm going to say int where. And then when I call it, I want to tell it, well, I'm going to start at 0. So now if I know where I am in the array, what's my base case? Yeah. Okay, well, but how do I use it? How do I write an if statement with it? So if I say if where is less than nums.length, that's actually good news, right? That means I'm inside of it. And so my base case actually winds up being in the else if I formulate it. So in the base case, Morgan suggested earlier, we could return 0. What about the recursion? What's this going to look like? What's W? Okay, how is incrementing where going to help me find the sum of the values in the array? So if I'm finding the sum of the values recursively, I know I need to involve a value somehow. How might I do that? Nums bracket where? You're right, Elijah. And I'm going to add this to something because I'm doing a sum. And what is that something going to look like? It's going to be the recursive call. And what are the parameters going to be for my recursive call? Nums is absolutely a parameter. Yes, yes. What about the other parameter? Where plus 1? Good, Paxton. Oh, interesting. So let me quickly add this up in my head. I think the sum is 29. And the program agrees with my mental math. Okay. So that works. Let's compare and contrast this with an iterative implementation. In fact, what I'm going to do is I'm going to rename this to be recursive sum. Oops. I don't want 2 S's. There we go. And now I'm going to write a method I'm going to call iterative sum. So for iterative sum, I've got my total, which I'll return at the end. And then I've got my for loop. And each time through, I add nums of I. All right. And just to show that they're doing the same thing, I will call iterative sum on nums. I will run it. And they both give 29. Okay. So that's all fine as far as it goes. What I want to do now is scoot back up and have you all look at them side by side. Metaphorically speaking, of course, they're not really next to each other. But looking at them like this, seeing them both at once, what do you all think are the pros and cons of each approach in terms of readability? Thoughts? Pros and cons for readability. You know what, let's take a vote. If you think the recursive one is easier to understand, raise your hand. 1. If you think the iterative one is easier to understand, raise your hand. All right, 6. Okay. Elijah, why don't you talk a little bit about what you found appealing about the recursive version?
I just think it's easier to look at it and see that like it's going through it, like rather than increasing each time. It's kind of like, okay, we're going here, like, on to the next one.
So it kind of brought into focus what it's doing each time, and you were able to develop a clear intuition of where it's going. Okay. Let's see. Ivy, what did you find appealing about the iterative version? Mm-hmm. So kind of what you found intuitive was first a familiarity with the meaning of the loop syntax, and secondly, the idea of accumulating, present there. Let's see. Paxton, what did you find intuitive about the iterative version?
It's just more familiar for me to read.
More familiar to read. As with many things that come down to clarity of exposition, there's no single correct answer here, right? It's entirely reasonable for one or the other approach to make more sense to you. And there's nothing wrong with having a preference either way in terms of clarity. That said, I do consider this extra parameter to be kind of annoying. In practice, that is often handled by having an extra helper method that's like the recursive kickoff. So you could do something like this. Recursive sum kickoff. And I would never actually name it that. It's an awful name, but it gets the idea across for pedagogical purposes. And where I might then say return recursive sum nums comma 0. And so this kicks off my recursive sum with an appropriate initial value for that extra parameter. And so that's a technique one can use to kind of clean up a recursion that looks kind of silly, as this one perhaps does. Any questions so far? Part of what we are going to do today is think about how does recursion work? How is it actually implemented? Where does the magic come from? There's a sense in which I think iterative solutions are often really appealing because the underlying instructions that the machine is executing are a little bit easier to discern. That is, I see I've got a for loop, it bumps this counter every time, so I can envision that there's some memory location for I, and then I gets plussed every time and the value's getting replaced. Whereas with recursion, it's like, oh, it called itself and then it like worked. You know, I mean, that's not really what's happening, right? But that's a mindset that's easy to kind of fall into. I want to talk a little bit about where this notion of magic might be coming from using kind of a classic of the recursion genre. So let's go back to IntelliJ to spell this one out. So here's sort of a classic of recursion. And it's considered a classic because it follows a certain mathematical definition very closely. And this would be the factorial function. So we'll jump back to the sketchy part. So if I've got this mathematical function n factorial, and the first time I saw this, which was probably in 7th grade, I saw that they were using an exclamation point. My first thought was, rats, they ran out of symbols. But anyway, so this is defined recursively by mathematicians, right? So it's kind of defined two ways. If n is equal to 0, n factorial is 1. Otherwise, it's equal to n times n minus 1 factorial. And that's the definition mathematicians use. It's a nice mathematical but highly recursive definition. And so it lends itself to a recursive implementation, which I'm now going to proceed to create. So as code, I would say something like this. If n equals 0, I return 1. Otherwise, I return n times factorial n minus 1. Like that. And, of course, I just can't help but call it. So let's have it do 5 factorial, which is 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120. Okay? Technically times 1 again, but I won't get into that. So I run it, and it's 120. Okay. But now let's really think for a moment about how the function works. So what's going to happen is I've got 5 factorial. And to calculate 5 factorial, I need to calculate 5 times 4 factorial. So now I need to calculate 4 factorial. And over here, we have a computation that has paused. It's just kind of sitting there, hoping someday, somehow, 4 factorial will become known. So now we have 4 times 3 factorial, and that too must pause. We get 3 times 2 factorial, and that too must pause. 2 times 1 factorial, that pauses. 1 times 0 factorial, that pauses. And now, when it comes time to evaluate 0 factorial, a nice simple solution jumps out at us. Why? Because this is the base case. We know that 0 factorial is 1. So now I can kind of go back down and fill in the missing pieces one at a time. So if 0 factorial is 1, this is 1 times 1, and that's 1. And if 1 factorial is 1, that's 2 times 1, and that's 2. And if 2 factorial is 2, that's 3 times 2, and that's 6. And if 3 factorial is 6, that's 4 times 6, which is 24. And then finally, I've got 5 times 24, which is 120. And somehow it's finished. But let's go back for a moment and think about the time before these evaluations completed. At that time, how many calls to factorial were simultaneously in existence? There were 6. You're right, Elijah. There was the 5 factorial, 4 factorial, 3 factorial, 2 factorial, 1 factorial, and 0 factorial calls. They all had to be in existence because every one that was further down was paused, waiting on a result from something that was higher up in the stack. Whoa, wait a minute. Did I just say stack? This is a stack. See, every time I have to pause a recursive computation, in effect, what I am doing is pushing that computation onto the top of a stack. And every time a function call completes, I'm actually popping that call from the stack. Just think about this for a moment. This isn't just about recursion, incidentally. This is how all function calls are implemented. What do I mean this isn't just about recursion? Let me show you something, right? So if I come back to main, for instance, if I call iterative sum, which doesn't involve any recursion at all, main still has to pause and wait for iterative sum to come back. And if iterative sum calls some function, iterative sum has to wait for that thing to come back. And now here is a key idea. The last function called is the first to return. You might remember on Tuesday I mentioned a stack is what's called a LIFO, data structure, last in, first out. Well, it turns out when you're dealing with function calls, last in, first out is the natural way to express the order in which they get completed. The last function you call has to be the first one to finish. Why? Because whoever called it is waiting desperately to find out what it's doing. So in light of this, recursion is an extremely clever exploitation. Oh, sure. Is an extremely clever exploitation of the fact that we use a stack to track what function is being executed and what other functions are depending on the values or even the side effects that it returns. Phrased differently, the magic of recursion is that we get a stack for free. We don't have to code the stack. That already was done for us by the creators of the Java virtual machine in a Java context. You might be wondering, well, what if you're programming in machine language? Where does your free stack come from then? Well, on some microprocessor architectures, the CPU itself sets up a stack for you to use very conveniently. The very first CPU in which I wrote assembly language, which was the 6510, embedded in the Commodore 64 of my fond childhood memory. Oh, that was a phenomenal computer.
For its time, yeah.
Yeah, for all time. So the machine language had an instruction that was a jump to a memory location, saving where the return address, where you came from. So what it would do is at the circuit level, when you called that instruction, it would look at where are you in memory. It would push that on the stack automatically, and then it would jump to wherever you designated. And then when you used a different instruction, RTS, which is the return instruction, it would just look at the top of the stack, pop it, and make that the new address in the program counter. So it actually did it on the circuit level, which is pretty cool. Some modern CPUs still do that. The Intel processors, for example. Some do not. The ARM processors, for example, actually don't provide you with a stack automatically, but their instruction set is set up to make it really easy to implement one, even in assembly language. So in any event, what you're getting from recursion then is a free stack. And what that free stack does is it stores these intermediate computations for you. So this has advantages and disadvantages. What we're going to find as we explore different kinds of data structures is that there are certain algorithms which cannot function without a stack. We're going to find this to be the case for a couple of state-of-the-art sorting algorithms. We're also going to find it to be the case for algorithms to navigate through a data structure called a search tree, which we'll be looking at as well. But there's also, intrinsic to this, a disadvantage to using recursion. Namely, the memory use of the stack. Let me show you what I mean. I'm going to show you by implementing an alternative iterative factorial. So for my iterative factorial, I'm going to code it something like this. Int total equals 1 for int I equals 0, I less than or equal to n. No. For I equals 1. Why did I suddenly stop when I put the 0 there? I was going to multiply it, yeah. That was not going to end well. I less than or equal to n, I plus plus. Oh, let's put a space in there. Total times equals I. Well, I. There. Return total. So that is my iterative implementation of factorial. And, I never really want to do anything without testing it. I want to tell you a funny story about that. In principle, it is possible for one to actually write a mathematical proof that a program works. Now, any of you that have had some practice with writing mathematical proofs might think, that's fascinating, but I bet that's a lot of work. To which I would say, you are correct. It is fascinating, and it is a lot of work. If any of you ever take Dr. Yorgi's functional programming class, that is a class in which you get to experience not only that process of proving a program correct, but also using some automated tools to accelerate the process, which is pretty cool. In the algorithms class, you definitely do lots of proving about whether a program works. And in the discrete mathematics class, all that gets set up, basically. So one of the, one might say the greatest computer scientist in history, whose name, so let me come back here. So this greatest computer scientist, his name is Don Knuth. Computer science being a relatively young field, this greatest computer scientist in history is still alive, in fact. He is old, he is in his 80s, but he's still around, actually. And once he had put together a program for something or other and sent it to a friend of his and then added a note of caution. He said, a word of warning, I have only proven it correct. I haven't tested it.
The program might not work properly.
The point being, he might have messed up the proof. The deeper point being, no matter how clever you think you are, you always need to have tested it. Because the tiniest error in your thinking will be ruthlessly discovered once it executes. And so you might as well find out now. That's the way I like to think about it. Okay. So anyway, my iterative factorial, it works beautifully. And so I want to bring it up for you all to look at for a moment. So the way it works is I set up this variable total, and I've got this iterative loop where I update total every time. So what I want to do now is visualize what this looks like within the machine, right? So if I'm calculating 5 factorial, whoops, I have total and I have I, right? And so, and I've got n. And so total is initially 1, and then I is 1, and then I times equal total. And now it's, I had to get to 2, and then total becomes 2. And I goes to 3, and total becomes 6. And I goes to 4, and total becomes 24. And I goes to 5, and total becomes 120. And the key idea here is throughout this process, I'm only altering really, or really employing in a substantive way, 2 memory locations. In the recursive implementation, I need to use a number of memory locations proportionate to the size of n. So speed-wise, they might be similar, but my recursive version proves to be what we might informally call a memory hog. It just gobbles up memory like nobody's business. So that's bad. Or is it, right? Sometimes it is, sometimes it's not. If you're creating an algorithm which needs to have a stack to operate, like I said, that includes some extremely important sorting algorithms and the like, then recursion isn't costing you anything because no matter what, you need the space. But if it's possible to implement it iteratively, recursion can use more space than is desirable. In fact, and I consider this in some ways an unfortunate design decision, but there it is. In a language like Java, they put a limit on how deep you can go in the stack. So I think it's something like 1,000. Python is similar. So there's a maximum stack depth. And if you exceed the stack depth, you get an exception known as a stack overflow. Anybody ever seen one of those guys? Yeah. So stack overflow means that you made too many function calls and they filled up all of the space that was initially available for the stack. Now, as we're going to discover, when we start talking about things like merge sort and quick sort and other algorithms that need a stack overflow turns out to be extremely unlikely with those algorithms for reasons we're going to examine. However, if we're thinking about something like the sum of an array, oh, silly touch screen, not quite doing what I need. There we go. If we think about something like the sum of an array, well, it is actually pretty easy to imagine having an array with 10,000 elements, and for that recursion causing a stack overflow. Note that the issue here isn't so much recursion as it is Java. That is, Java was not designed with the idea of rigorous support of recursion as one of its design criteria. It's just not what the designers were trying to achieve. Other languages are designed to support recursion well. So for instance, the Haskell language that Dr. Yorgi teaches in functional programming and programming languages is in fact designed to support recursion well. And so you think about it differently because the language is designed to support it differently. But Java is not, it's safe to say. So this certainly doesn't mean never use recursion. In fact, when it's clear, I often highly recommend using recursion. I just want you to be aware of its limitations, you know. I'm personally kind of fond of recursion. But there is this issue with the stack. Any questions so far before I talk a little bit more about the program stack as it's known? All right, cool. So let's think a little bit more about this idea of the program stack. Back here, when I was talking about factorial, I may have conveyed the impression that the information about the function only gets pushed when something else gets called. That was a bit of a hand-wavy simplification. The truth of the matter is, anytime a function is called, starting with main, information about it immediately goes on the stack. So as soon as I create something like main, as soon as main gets called, there is information about main that's already on the stack. Now, what kind of information, you might wonder, would this include? The number one thing this includes is the parameters and the local variables associated with main. So when it gets invoked, all of the parameters are immediately copied onto the stack, onto the top of the stack. They're all pushed right on the stack. And then every time you create a local variable, it's also pushed on the stack. It actually gets even crazier than this. Anytime you open a curly brace, a new stack frame is set up. So think about how when you open a curly brace, you can declare a local variable that goes away at the end of the curly brace. What's happening is when you open the curly brace, it sets up a new frame on top of the stack. And it's got all the local variables from that curly brace. When you get to the closing curly brace, what it does is it pops everything off. To be absolutely clear, it doesn't just pop everything off. In fact, what it does is the top of the stack is tracked by a special variable called a stack pointer. It actually just tracks how many things do I have on top, and it just subtracts that number from the stack pointer. So basically, in one instruction, it pops everything off the stack that was associated with that frame. So part of the point of this is thinking back to our discussion last week about memory and allocation in the stack and on the heap. I hope this clarifies, what we mean by stack allocation. That is, if I have stack allocated memory, what that means is it is information stored in a variable which is in the stack frame of a function call. So stack allocation means data is stored in the stack frame of a function call. Now note that depending on how you swing this, right, something that's stack allocated can last a really long time. Like a local variable in main is going to last for the whole program, because once main gets popped from the stack, the program's over. It's done. Right? But anything that gets stack allocated from something that's a few calls in has a very limited lifetime, right? It cannot last longer than that function call. Once that function call ends, it's gone. This has an important advantage and a highly distressing disadvantage. The pro it is easy to clean up. That is, you've got all these stack allocated local variables in your function. Once the function ends, you don't have to do any work to release the memory. The stack pointer gets reset, and the next time there's a call, it's all going to get overwritten. Life is good. You just go pop, 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 pop. And there it is. As the programmer, you don't have to do any work to clean it up. Con is nothing lasts, right? Let's say, for instance, I do some kind of a function call in which I create an elaborate data structure which I want to return so it can be used later on. Well, the trouble is, if all that data is on the stack, when that function ends, it all just goes poof, gone. And that's why we need a heap. The heap is persistent storage. That is, once you allocate something in the heap, it's there, right? But it's really fascinating how we have a certain duality here. Either things can last and they're hard to clean up, or things don't last and they're easy to clean up. So which is better? Depends on what you need, right? If you don't need it to last, use the stack. If you do need it to last, you use the heap. And the way Java is set up, Java assumes you're going to make massive use of the heap. Massive use of the heap. Anytime we call new, that means we are allocating in the heap. Anytime we use new. So that's really valuable to know. Anytime you use new, you're setting up memory that's meant to last. I won't go over the details today, but one convenient way to think about this is when I say Java is optimized, assuming you're using the heap a lot, what they do is they do something really clever, which makes it so that, see, in practice, when people use new, the things they create with new either die really, really quickly. That is, the only live reference to them is from a local variable on the stack. Or they tend to live a really long time, like most of the duration of the program. There isn't a whole lot in between. So Java has done the Java virtual machine does some really clever things to very quickly clean up heap items that have short lifetimes. Very, very quickly. And then for the ones with long lifetimes, have a minimum of overhead. So again, each language has its own context. In the context of Java, we go ahead and we use the heap pretty freely because that's how the language is designed. That's what they have in mind for what programmers are going to be doing. So, and to that end, they do all the work to clean up the heap so that you don't have to. Cool. That was a lot to swallow today. But I think we hit a lot of important ideas, and I hope that you gain some real clarity on why the idea of a stack is such a central idea in computer science. It all comes down to, in programs we write, the heart of the execution model is this idea of a function call, and representing those function calls is most naturally undertaken with a stack. Cool. I will see you all Monday.